Okay, we all know each other, but just to repeat, I'm Marina, I'm CTO of Veles, and today together with me is also Žarko, who is the CEO of Veles. And in a past year, we work on Divine project, which is discovering invisible wine nutrition elements. So we are startup from Serbia. We started 3 years ago, a little bit more than 3 years ago. We have three core members. So I have a PhD in digital image processing and more than 7 years of experience after a PhD. So I'm a technical person, let's say. Žarko, he is in charge for sales and marketing, but he's also drone pilot. So he's the one who is on the ground talking with vineyard owners, but also collecting data, labeling data, and having communication with the domain experts. In Veles, we are developing several solutions. Our main solution is for disease detection, and we are targeting one specific disease called ESCA. We also do some monitoring of water stress, and in this project, we were focused on nutrition deficiency. So we tried to distinguish between diseases and nutrition deficiency if possible, and we targeted organic vineyards. So we had four main objectives. So the first and let's say the final goal was to design a pipeline. So the full pipeline, how you can start from collecting images with drone and then detecting a disease, and from what is, let's say, rest, try to detect nutrition deficiency. So the main idea was to design this pipeline that can be used later also for the whole process of nutrition deficiency detection. Together with the pipeline, we implemented parts in a user-friendly interface. So we have a web application that users can also upload their own drone images. So this is also for us as a company that we don't need always to use our own drone, but we have now a web application where users can, following of course some of our let's say parameters for drone imaging, they can collect their own data and upload. We did a nutrition deficiency assessment, and we integrated remote sensing and ground data. So we defined two use case scenarios. First one is vineyard stress detection, including both disease detection and detection of the nutrition deficiency. And the second use case is quality prediction of overall vineyard. So the full map of overall vineyard. And this is what we did in 1 year. So as you probably know, we are, let's say, connected with the season. So all the data collection, new data and samples collection need to be done in a season, which in Serbia is June, July, August, maybe beginning of September sometimes. So at the beginning, before the season started, we did a lot of, let's say, planning. We designed the full pipeline. We designed image processing algorithm using the data from the previous season, so data that we already had. And also we did a full design of a web application. And then, of course, when the season allowed, we started with collecting data and testing the computer vision machine learning methods that were developed, and of course, collecting samples and doing analysis. Last part was dedicated to sales and marketing activities. We did marketing activities through all the project, of course, but at the end, we also tried to present what is done in the season 2025 and what we have so far. This is the equipment that we have. So the main, let's say, the most important part is the drone, which we use DJI Mavic 3 multispectral. We have Vertica mobile station for precise geolocation, and also we have in-house GPU with 24 gigabytes for all the machine learning tasks. So we don't need to use servers. We have it in-house. We use commercial software Pix4D to create ortho mosaics and orthophoto. and of course Python programming language. This is just uh, requirement techniques. So for orthomosaics, I mentioned Pix4D. For disease detection, we use proprietary software of Veles. Of course, I mean, the pipeline is created such that any other disease detection method can be plugged in and used. We, of course, choose to use what we have. Additionally, and you will see later more details, we created some Python scripts that were necessary to cover the full pipeline. So this was the main idea. This is how the pipeline is designed. So at the beginning, we started with, let's say, collecting images and both images and ground truth. So for just info for everyone who works with disease detection with drones, it's almost impossible to do labeling directly on the image. So the drone is flying on, in our case, on 30 meters, which is the, let's say, some optimum between the battery usage and the coverage of the area that we want to have. And from 30 meters drone images, for experts, it's extremely difficult to label images. That's why we do labeling directly in the field. So we are posting some marks directly in the field. It's labor intensive, but it's necessary in order to have a proper ground truth. When you label images, of course, you need to do stitching, and this is something that was quite painful for me when I realized that I cannot create my own stitching algorithm, that I need to use commercial. That's because the DJI is not opening metadata, but that's another story. Then we needed to develop approach for, we call it here plant counting, but that's basically detection of wine locations. So I wanted to know exact location of each wine. When we planned for this, I was thinking that this is easy task. It's not. It's one of the open questions in research with drones, especially vineyards, because you're collecting images from above and your vines are interconnected. So it's extremely difficult even for the human eye to distinguish between two neighboring vines. Then we did the first preliminary maps, vegetation indices that we usually use. This is done on the whole map, but also with the extraction of region of interest, so I don't have interference from everything that is going on around. And then once when you do vegetation index, you see where you have zones with some changes, with stress. Then you remove with disease detection what you detect as a disease and do sampling on the what is rest to figure out whether there is a nutrition deficiency or not. As I mentioned, there were some during the project. There were some, let's say, auxiliary Python scripts that we needed to develop. So first one was when you do disease detection. Usually, you have these bounding boxes, which are quite let's say invisible for the human eye and very hard to transfer on the full map. So the first, let's say, small task I created from the bounding box, I tried to create visual representation of a disease. In our case, for disease detection, we are detecting three things. So one is ESCA, the disease. The second is maybe ESCA, so there are some symptoms, but we are not 100% sure. And the third thing is everything else. So we have three labels. Everything that is suspicious and the method detects, but it's not ESCA, it labels as other. This is the results of a method for wine detection. As I mentioned, that was quite challenging because in order to create really like full machine learning, a neural network, vine detection elements, I mean, the model, you need a lot of label data, and it cannot be just for one type of vineyards. So it need to be vineyards with the grass in between, vineyard with the bare soil in between, on the hill. Then I tried some existing methods, and it was somehow overkill because usually existing methods are trying to figure out all the vines, so every leaf that is inside the bounding box. And for me, I only needed the location. So I don't need like the full vine, I just need the location of the vine. Then, as I mentioned, we created a small script for raw extraction. So again, I put all the scripts available on GitHub. It's not something extremely difficult, but it's useful. So you don't need to use cookies or some extra software. You can run a Python script and extract your region of interest. And then the sampling results. So the sampling is done in May, where we try to do referent values, and then we repeated sampling after data collection in July. This is organic vineyard, so there were some problems that we expected to have. The sampling is also quite labor intensive. Usually you need also I mean, expert in the field to help you with the sampling. And depending on the analysis, sometimes you need to collect like 150 stems in order to do one sample analysis. This is what we did in May, and then in July we used another laboratory, and it took 20 stems, 20 leaves per analysis. These are results of the analysis for these specific vineyards. So I will go back one more. So we have four region of interest, and the analysis show that okay, that the iron is missing in all four. Uh, and the copper is, let's say, excess of copper is in one region, uh, and this is not really visible on the map, and you will see later. As I mentioned, yeah, we created additional user-friendly interface where someone else, so not necessarily us, can upload drone images, raw drone images. Uh, when they upload drone images, they can also choose which type of service they want. We implemented for now vegetation index calculation and plant counting. Uh, the user can add some additional options, and when the data are uploaded, we receive the email with a message that says that we can download data. And this helps us a lot in our work in order, I mean, especially for the future when we want to go beyond Serbia and do some imaging in Italy, Portugal, Spain, and France. This is results of a clustering method. So basically, I wanted from the vegetation image map that we usually saw to have to extract some clusters, and I use very well known methods to do it. And why I wanted to do this, it's also because in a final map, I wanted to see whether I have problems on a map and where I have a ground, which is usually something that is quite, let's say, distinguishable on a vegetation index map. And basically, this is the final map. And here I want to say something interesting. So earlier, when I mentioned ESCA detection algorithm, you saw a lot of blue and red marks. So blue was ESCA and red was maybe ESCA. And now we have green map, the labels. And this is because for this vineyard, this is small organic vineyard, the owner told us that he had problem with ESCA, and this is why we choose the vineyard. But we went into a vineyard with our own expert he said it's not SK, it's some other disease. So we needed to label it as other. So this is one of the, let's say, uh, once when you go beyond research and start to use your own solution, this is something that will happen definitely. What are challenges? So first, georeferencing of all our maps needed to be done manually. So even if we have RTK, the maps are moving a little bit, so we needed manually to have some markers. In some vineyards, it was easy because you have also some houses and some elements that are not moving, but in some other vineyards, you needed to put your own marks. For automatic wine detection, as I mentioned, in our case, it's not fully supervised because we didn't really have time to collect and label a lot of data. So I now call it semi-automatic wine detection because it asks for some additional information before it does wine detection. We did lab analysis in two different laboratories because when we sent the first sample in a first laboratory in University of Belgrade, it took us more than a month for the results, and already we were starting to panic because the season was going off. So for the next lab, we choose another lab from the institute in Novi Sad, and the results came faster and they came quite different. So our expert believes that the second results are more reliable. The impact, so for impact on rural areas, especially in Serbia, we are fully aligned with smart specialization strategy, which is strategy that is now ongoing in Serbia until 2027. Again, the results of a project can have a financial impact, also economic resilience, but also promoting sustainability practices and supporting market growth. For environmental impact, again, we are aligned with the From Farm to Fork strategy, which says that until 2030, the amount of fertilizers and pesticides need to be downsized to 50%. So we are supporting with our small project that goal. For replicability, so all the pipeline design Python codes, they are on GitHub, data on Zenodo. With the data we are sharing, so we are not sharing raw images, we are sharing maps, but also ground truth and sampling results for everyone who want to reuse it. Just at the end, some communication and dissemination activities. So we were two times at national television, TV in a morning show. So first time I was in a studio, and the second time Žarko was he was from the technological fair in Belgrade, and in both we had opportunity to mention EU fundings. We representing our results on ESCA detection and other types of services that we have in Moldova are on Wine and Wine Symposium, and it was quite well received. Also, I give a short presentation in Beijing, in China, where we presented, among others, ICAERUS project, the results of the ICAERUS project. And our next steps, so the main steps is to test this full pipeline on more sites. So during the project, we had opportunity to test two organic vineyards, but we need, of course, more in order to see whether the results are reliable. We also have in-house thermal camera on a drone, so we want to co-register with thermal data to see whether some causes of stress are water stress and not nutrition deficiency, which is more and more often in next years, unfortunately. We want to create a data set for automatic wine extraction. We think it's quite important. It will take some time, but it's crucial to know exact location of the wine. And of course, we have a business related activities, and currently I'm in Serbia, but Žarko is in Portugal because we are trying to open a new market in Portugal in next period. And thank you. That would be all from me.
So I will present gprSense. So first about SENSAR Consulting, I created the company as a complementary activity to my activity at the university in 2012. And the main scope was to perform services, expert services with ground penetrating radar and electromagnetic induction for high resolution subsurface imaging for applications like in agriculture, including in vineyards, in archaeology, or for utility detection. And then in 2020, more or less, I started the development of gprSense. So basically, to manufacture a ground penetrating radar and software for first application soil moisture mapping. And then in 2021, I was funded by the European Agro-Food Mirage project together with Osiris Agriculture in France with the irrigation robot that you can see here. And the idea was to mount the radar system in front of the robot to optimize irrigation by providing a real-time soil moisture. So for this OCT, the objective was to basically advance gprSense from TRL 8 to the final product TRL 9 by working on different aspects, including the hardware, the software, but also by validating and performing field measurements and also preparing for commercialization. And so within this OCT, I defined basically two gprSense models, LF for low frequency model that is mainly dedicated for digital soil mapping, including a root zone soil moisture mapping. So we are in the low frequencies. And then a high frequency system for high resolution shallow subsurface imaging, including shallow soil moisture mapping, which is also useful not only for agriculture, but also for calibrating satellite remote sensing data products of soil moisture, so for upscaling. And so, of course, with these two radar units that we can cover the full possible GPR frequency ranges, there are also other applications, as I will present afterwards. So the specific objectives, as I said, there is an objective was related to the hardware refinement, but more development than refinement actually, including the enclosure and design of all the content with the electronics and also radio frequency components. Then regarding the software, it needed also to be further developed with solving for bugs, including a series of new features, making it ergonomic, real-time processing, and so on. Then a third specific objective was to apply the instrument in field validations in different contexts, in different agricultural fields, and also in terms of making the tool commercially ready. So the key activities and timeline I illustrated here. So the hardware development mainly focused on the 3D printing by the choice of the materials. So I needed to test different materials and also tune the printer settings for the quality of the enclosure. Then in terms of software development, so that was the second component. And it was initiated within the framework of this project based on a request from a client, the development of the high frequency model. And then a task was the integration of all these components, so the software together with the hardware and configuration of the radar computer to be ready for the field trials with the drones mainly, but also with some robots, as I will show you afterwards. Then this summer, I created a major support, which is the user manual, but also training materials for the clients. The website was launched in January of this year. It has to be further developed with case studies, but it's already quite complete to present the product, and then a series of outreach activities. And so the timeline looks like a direct timeline, but basically it was like a loop by working on the hardware, then the software, and so on, making the field trials, and then getting feedbacks to improve the whole systems. Also, I get feedbacks from potential clients or stakeholders to add the new features they were interested in. So this was also very useful for the product development. So on this picture, you see the two models in operation. On the left, the low frequency model for root zone soil moisture. With in the background, my PhD student at the University of Merlin, who is working a lot with these instruments and gprSense. And on the right, you see a video um, of the high frequency radar system mounted on a small robot from the Royal Military Academy for landmine detection. So this is really operational, and they're still working on the robot. So that's why you see a series of strings and so on, but it's already operational. And last week they were in Sweden for making tests with other people and scientists working for landmine detections. So the radar is really ergonomic and lightweight, so it can be mounted on a drone easily with easy integration because it works independently and also can be fixed with a quick release. And for the drone, a major requirement is to have a drone that has a terrain following capability, but with really close range terrain following. So it needs another radar system or LiDAR on the drone because we have to follow the terrain at about 1 or 2 meters height above the ground or eventually slightly higher. Oops. Yeah, so I'm here. So in terms of data and drone data analytics models, so you see here on the right a screenshot of the GPR interface where you can display different variables, including soil moisture. So this is a root zone soil moisture map on a test site in Belgium that is showcasing viability, that also justifying the need for mapping soil moisture with also nice spatial correlations with areas that are drier and may require irrigation and areas, let's say, that may not need irrigation. And so what makes the instruments unique and also very strong, it is the fact that it is based on full wave electromagnetic model and also a vector network analyzer technology, which means that the data we provide are fully normalized and calibrated. And within the project, I even further developed a temperature-dependent radar calibration model to account for the temperature drift of the system, which means that the data are fully normalized and independent of the radar. So different radars would provide the same data. And nowadays, this is very useful for applications where artificial intelligence is used because by using normalized data, you can really train your artificial intelligence and apply it to different systems. So the soil moisture is estimated using what we call full wave inversion, which means we fit the electromagnetic model to the data. This is theoretically the best that can be done in terms of parameter retrieval capabilities, in terms of quantity of information, but also quality. There is real-time processing capabilities and even real-time data streaming for on-the-fly applications like providing the soil moisture to the irrigation robot. And also there is, of course, post-processing that is possible if the user want to tune different processing parameters. The data open access, so these are just ASCII files in text format, so the user can access to the raw data, which may be useful for scientists who want to deepen either the electromagnetic data or the map. So this is fully open access. And also, the software can be updated with the application. So the user can just click on a button to update his software to the new version. And this is also encrypted. So this is a protected update. So only allowed users can update the system. In terms of major outcomes of the project, so we can say that TRL9 was reached with both the low frequency and high frequency models. A robust hardware was built with IP65 enclosure, which is made for outdoor conditions. The software reached version 1, which means it is fully operational with the user interface, automated calibration, real-time processing, also advanced imaging, so new features that was added, data streaming and updates. So during the project, I conducted between 20 and 30 field trials mappings in collaboration with the Université Catholique de Louvain, where I also work, the Agronomic Research Center of Jean Blou, then the University of Ghent, and also Osiris Agriculture with manufacturing the irrigation robot. And the most major milestone, I would say, within this project was the first commercial sale of gprSense to the Royal Military Academy of Belgium for the application of landmine detection. So they are running the radar since May. Until now, everything is going well. So I'm very happy that the hardware and software are both working. Of course, a few times I had to provide support to help or choose the parameters or solve some issues they had, but everything is working well. So in terms of market readiness, so the website was launched. I could get the European IPO trademark. So now gprSense, it's a European trademark. And something that is also important, and that was quite a major step as well, is to build a user manual that at the end turned out to be 75 pages with details about everything, including the theory behind. So which means that the radar is not a black box. The detailed equations are also provided, and let's say the scheme of the processing, everything is explained in details. And so in terms of outreach and visibility, I was invited to provide 2 keynote lectures in 2 international conferences, GPSS in Belgium on proximal soil sensing, and as well at the SEG Drone Geophysics conference that was held online. And during the GPSS conference, I was invited also to give demonstration and real field demonstration with the drone and gprSense. And for both events, there was about 75 people coming from all over the world. So it was quite a nice outreach. So the challenges faced, significant time was dedicated to the 3D printing by choosing the appropriate plastic for the 3D printing, because we have to respect a series of criteria in terms of strength, color that should be right to reflect the light for the temperature management, for instance, aesthetic, and also printability. And so this was really a challenge to test a series of materials. And at the end, I could choose the Polymax Tough PETG, which is a plastic that can be also recycled, that do not, during printing, make smokes that are not good for health. and then I, let's say, optimize the printer settings for that. Another issue, which was the temperature sensitivity of the radar measurements. So sometimes I had not stable calibration, so not good results. And I solved that by developing a new radar calibration model, which is fully electromagnetic model, not published yet, but it turned out to be very effective. So now the temperature effects are accounted for. Some difficulties were related and are still with respect to the component sourcing, because some component like the battery, the manufacturer is changing a few things, so I have to make adaptations, and also some electronic components that do not perform exactly in the same way. So I have to make small adjustments, but thanks to the 3D printing, I can really adapt rapidly the plan and just print the updated box. So it's very fast and very modular, I would say, with the 3D printing. So it has challenges, but now everything is tuned. It's really a benefit. And then during the winter period, there was a drone downtime because the drone has some issues and had maintenance. But it was during winter, so anyway, not too much field campaigns planned. And then I used that period to mainly work on the hardware. In terms of impact, as you saw from the map, the soil moisture variability can be very significant at the field scale. So characterizing that variability with a high spatial resolution can lead to water saving of more than 30%. We can see that in the data in this project, but it was demonstrated already in the previous European project, which is very significant. Then, of course, in terms of climate resilience, it's also beneficial to better face drought and heat waves. The method is fully non-invasive, which is good for the preservation of the soil. And also by decreasing the amount of irrigation, then inherently we will lower leaching and runoff of agrochemicals or nutrients. On a broader impact, so the socioeconomic and humanitarian value of the technology, the idea is to provide higher yields with fewer resources, so with less water. Then in terms of capacity building, because this is a new tool that did not exist on the market, it will provide to scientists and farmers information that was simply not available before. Before you had no high resolution root zone soil moisture map that you can acquire non-destructively, let's say. There is also for humanitarian demining a very important application there. And this is highlighted here by the fact that now the Royal Military Academy of Belgium is using it in its project on landmine detection. And of course, there's the overall global relevance at the country level, but the European level as well, because all of that is aligned with the Sustainable Development Goals, the Green Deal and Soil Strategy, and also water directives. So in terms of replicability, basically all the technology, let's say, with the standardized full wave inversion has been subject within my research team at the university to more than 25 years of peer-reviewed research and publications. And now everything is integrated in gprSense. As I said, the hardware is really modular, so we can adapt it easily to different platforms. It's also lightweight. The calibration protocols are also programmed and repeatable by performing with the radar measurements over reference surfaces like a water body, like a lake for the drone-borne radar, or a copper sheet in the lab conditions for the high-frequency radar. So the system is fully calibrated, which makes the data standardized. Then also, thanks to the fact that the hardware is integrated with the software, it makes a unified acquisition and processing. And this fact is very important because in the scientific world, this really limited the use of, let's say, this approach by other scientists because it's not so easy. And now everything is integrated properly. Then it makes it really replicable by others. And then, of course, there is this 75-page user manual that details everything, and the data are open access. So as a conclusion, so the main conclusions are that TRL9 for both models is reached with both hardware and software reaching version 1. And then, as I said, the first commercial sale was done with the Royal Military Academy. And then during the conferences and events, or even by email, I received strong scientific and market interest. So now the next steps are to manufacture demonstration units because the future clients are requesting to make demonstrations. And so now I'm manufacturing the low frequency and high frequency units. And actually, last week, I could complete the manufacturing of the low frequency unit. I still have to calibrate it, but this is done. In terms of software, I'm also using these few months to upgrade the software by adding new features and making some refinements to make it better even for the official product release. I plan it on 1st of January, but of course I could already agree on sales at this moment because I have already something version 1, let's say. For next year, I would like to sell between 2 and 4 GPR systems. And actually, in addition to the particular interest that I had from a few people, we included gprSense within a scientific project. 2 units are included in a European project that we submitted 1 month ago. 1 unit is included in a project from Aarhus University in France, and another unit is included in a project, a national project on decarbonization. So I don't know if this project will be funded or not, but these will be first potential units for sale, and which is very interesting because it would be in the frame of scientific research. And at this stage, it's good to start the commercialization at that level, although with Osiris Agriculture and the irrigation robot, there would be potentially sales to farmers. And I will wait maybe 1 more year to get and apply for international certifications to sell it outside Europe. I wait for that time because my production capacity is limited, but also because the instruments may still know some improvements or small changes, and it's better to apply for these certifications while once the instruments is not subject to no more changes. And so here you see really the radar in the box. This was just before, that picture is just before the delivery to the Royal Military Academy. And so thank you very much for your attention, and also thank you very much for this funding, which was quite a unique opportunity to make the last boost to gprSense because it provided not only the funding, but also a framework and also a timeline to progress continuously in that project. And so this was really a key project for the development of gprSense. So thank you very much.
All right. So I'm going to present the results of Optivery. And first is the introduction of ITG, our technology center. We're a national technology center recognized by some institutions in Spain. And we have been established in 1991, so we're relatively young. We have different areas of work from smart energy, digital water, sustainable construction, AI and ICT, and IoT and autonomous mobility. So for Optivery, the departments that were involved in the project were my department, which is the one on autonomous mobility, and the IoT department, which they were the ones that were in charge of doing the optimization algorithm that I'm going to show later. So Optivery, it came across basically from a conversation that we had with Sergas, which is the healthcare provider here in Galicia, in the region of Galicia. We collaborate with them a lot, or we try to provide solutions for them that make sense from our areas of expertise. And in this case, they told us about the situation that they had, which was that a lot of people go weekly to the hospital. So the hospitals are mostly located. I don't know if you can see my the cursor, but basically the hospitals are located mostly along the coast. So this is the Atlantic coast. And so people usually have to move from rural areas to the hospital to take medications that can only be provided there weekly, because the rural healthcare centers that are in these other areas, they don't have the capacity to do that. So something that we came up with to solve this, to see if this could be a solution, would be to have a drone delivery service that would go from main hospitals to rural healthcare centers to give these medicines to population living there, and avoid this transportation that they have to make every week from their location to the hospital, and also help to the hospitals with overcrowded situations and helping in capacity as well. So this was basically what Optivery was trying to solve, and the specific objectives then were to develop and demonstrate this multi-stop optimization algorithm to provide these medicines from the main hospital to the rural healthcare centers. So the objective was basically divided in three. So first, to develop and integrate this multi-stop route optimization algorithm, then demonstrate it in a pilot project, and then assess the techno-economic viability and market opportunities of this. So scenarios that we did, these are screenshots from DroneSuite, which is the platform that we use to control all the flights and where the algorithm was integrated in. So this is the simulated scenario, and on the right is the real scenario that we flew. We did it in Ce, which is a location in the northwest in the coast. The location was chosen because it would be easier in terms of permits, the flight permits. We still had issues. I will talk about that later. But it was just kind of like a trial scenario, and just to showcase how the algorithm would work. And also, this was a location that was interesting for Sergas, the healthcare provider. So that's why we chose this location. And as I said, this is the simulation scenario, just like a screenshot. And here on the right, you can see the route that was flown in the end in the final demo. The activities that we performed in the project, you can see them in the slide. So we divided in three, as it was asked, I think, in the project: design, development, and market phase. In the design phase, we worked on the concept of operations, the regulation requirements, and the baseline for the algorithm. So in the ConOps, basically what we did was understanding what would be the mission, how it would be flown, what are the stakeholders that are involved, and the type of flights that would have to be performed, basically. In the regulation, we checked both the flight permits and just aviation regulation that is needed for this type of service. But then also we had a check with Sergas about the medication specifications and things that are needed to be in check for this, because maybe the medicine needs to be like at a certain temperature, or it cannot be out of certain situations for more than X time. So these kind of things we checked. And then the team that was working on the algorithm started to define the requirements and the baseline for this. In the development phase, we did the development of the algorithm. We integrated the algorithm in Drone Suite, which is the platform that I showed before. So the screenshots, that's the Drone Suite platform. We worked on the permits, so on acquiring the flight permits to do the final demonstration. And then we also did the validation. The validation in the end actually went a little bit more into the market phase in terms of like timings, because of some issues that we ran into, but it was supposed to be in the development phase, which should have ended, I think, in June. But things happen. And then the stakeholder engagement, we also did it in here. So throughout all the timeline of the project and the activities, we had periodic checkups with Sergas, with Blueness, and with Servicio Móvil, which were the companies that were kind of like advising us on the project because of their interest. So we had regular checkups with them to see if we needed to consult any information, like we did for the regulation part, for instance, or things about the market plan, economic interest, and this kind of stuff. So that was in the development phase, and then in the market phase, we just did the economic viability of the solution. Regarding the technological requirements and guidelines, the platforms that we used, it was the DJI Matrix and Drone Suite, which I already mentioned. These are pictures from the demonstration day that we had at the end of August in FE. And so, yeah, we just use this DJI Matrix. And here you can see on the right side, this picture is Drone Suite, which is basically also mounted on, how can I say this? Like a control center, a mobile control center, from which we can just basically operate the drones, and we can control all our technology and manage operations from there. Regarding the data models, here you have the two algorithms that we used. So we used two algorithms. The first one is the 3D drone routing algorithm, with which we generated the flight paths between the different locations that were chosen. It computes the 3D routes considering both terrain elevation and no-fly zones. And what it does is basically to find the most direct trajectory between the points that are chosen in the algorithm. The no-fly zones, these are taken also from just data from ENAIRE, which is the ANSP, the Air Navigation Service Provider in Spain, and it provides the data about places that you cannot fly over. And then the vehicle routing optimization algorithm was used for the delivery sequencing. So after finding the most direct trajectory, then this second algorithm determines the optimal sequence in which the delivery should be made. It considers all the possible combinations of deliveries from the base point to the final delivery point. And it minimizes the total travel distance while respecting the payload capacity and battery autonomy. So the optimization problem was solved using a genetic algorithm. And the approach of using two different algorithms was just basically to allow some flexibility to explore the possible delivery sequences and also to allow situations with many constraints and changing inputs. The outcomes that we have, it's basically what we already discussed before, which is the optimization algorithm. So we were able to deliver this multi-step optimization algorithm that is capable of optimizing routes for time, energy, and to serve the highest amount of healthcare centers in one trip. We have the medical drone service, so minimum viable product that was also validated in this demonstration with our advisory board members that were Sergas, Servimóvil, and Blue Nest to provide this service from the hospital to the rural healthcare centers, and then to have an initial business plan that was discussed with these companies. And we're actually continuing to explore the business plan through another project, a follow-up project that we're currently developing. And we're also continuing to develop the MVP for the drone service. So these two things we finished in this project with the initial phase, but then a follow-up project came and we're continuing these two things over there. The challenges that we faced, on one hand, we had like some challenges on the algorithm. So regarding the drone battery consumption, there wasn't any function to model it. So we had to basically come up with our own model to do this manually. And this was a bit more difficult, but we basically did it manually, defining the wind speed and the load ranges based on other projects that we had and experience from past projects. And also we had some limited experience solving this type of algorithms. So it was kind of like first time kind of. So to avoid any issues, what we did was to implement the algorithm in different phases. So we had first an algorithm that would solve the problem for time, then for energy, and then we did the battery capacity in the end. And then also there were some challenges regarding the optimization of the routes in a 3D space, because it just basically presents more computational challenges. And then regarding the flight trials, we had some difficulties as well, as I mentioned before, coordinating with authorities. So in the beginning, we thought it would be pretty easy because it was an area, the place where we're going to do the demo. So, in theory, we didn't have any airport nearby. There weren't like any very specific flight permits that we needed to acquire with a lot of time in advance, because the drone that we were flying with, it was just not complex enough to require these things. So we thought it would be pretty straightforward. But then in the end, there were some problems, more than regarding with the flight permits. It was more with the police, because the thing was we were flying over water, and it was an area that was there was a beach nearby. There are people walking nearby. There were boats. There was a port. So we needed to have a police boat in the area of the water to make sure that there weren't any boats entering or exiting the area that we were flying in. So for this, we did a lot of conversations with the police department, with the regional government in Galicia. And I don't know what happened in the end, but the permits, the conversations were lost somewhere. So the police, when it had to be there, they weren't there. So then we had to move the flights to later on in the summer. So this was initially scheduled for June, and then we had to move it to August in order to have the boat from the police to monitor this water area. Then also we had the lengthy process to get the flights approved. So we started already in February, I think, to see what were the possible flight routes, the areas, acquire the permit. So that, of course, was I would say not a challenge per se, because we knew that this would be something that we had to do with enough time, but still it's something that you need to take into account, and it was a lengthy process. And then another thing that could have been an issue, and in the end, thankfully it wasn't, it's the weather, because I don't know if you see it, but in one of these pictures, you can see that it's very cloudy. And this was in August. So we weren't counting with this weather in summer. In Galicia, it rains a lot, but not as much in summer. So the day before the flights, we did some trials, and that day was super sunny. But the weather forecast for that day, it was really rainy and with a lot of wind. So we were a bit scared, because it would have meant that maybe we had to reschedule again, and we wouldn't have been able to fly. But thankfully, it was fine. It didn't rain. The wind, it was perfectly within the capabilities of the drone, so no issues there. But we were scared for a hot minute. So there, regarding the impact, regarding the socioeconomic impact, we had some impact regarding techno-economic development of Galicia. Thanks to developing this drone service, we would be able to basically foster innovation in rural areas and create new job opportunities with drone technology. Then also we provided improved medication access in rural areas. With the service, we would be able to serve these areas, and then people wouldn't have to go all the way to the main cities in order to be able to be served. And then also improved quality of life in Galicia because of these things. So rural areas, they can experience this in improved accessibility to healthcare, better quality of healthcare in all Galicia, and also timely and appropriate treatments could be served in rural areas and also in the city areas. Regarding the economic impact for ITG, I mean, this is not something that is finalized yet, but in case that we are able in the future to deploy this service, this would mean probably around 30K from licensing a cloud management from Drone Suite. Then for Servicio Móvil and Blue Nest, 160K approximately from the provision of services to Sergas. And then for Sergas, it would mean a reduction in congestion and workload in the hospital. So these are numbers that we worked out with these companies. They are not final. These are things that we also discussed in the economic viability deliverable, I think. But these are things that we're still working out now, as I said, in this follow-up project that we're currently working on. And then regarding the environmental impact, we have efficient resource allocation, thanks to an efficient use of time, energy, and manpower through the deployment of this drone service, and also in result of this, an improved operational efficiency. Then also reduction of CO2 emissions, thanks to the elimination of the transport of the patients from their locations, from their houses to the hospital and back. And then air quality improvement as well, from the elimination of the road transport that occurs when people go from one place to the other for the hospital, and also an improvement of the health in general for the Galician community, thanks to this better access to healthcare in all locations. In terms of replicability, we have these 4 things. So the multi-stop optimization algorithm, it could be applied to other industries and other use cases. Anywhere where you need an optimization of the flight plan for multiple locations, I think this can be used. And we will use it in future projects, even if it's in different industries than the drone industry. Drone Suite as well. So this software can be used in other industries and use cases. We usually use it only for drone projects and drone services and use cases, but we are starting to expand the use of Drone Suite to other industries and to be able to serve, for instance, the management of operations for different technologies. So a combination of drones and road transport, or drones, road transport and maritime transport. So basically we're evolving it towards multi-transport management software. So this can be also applied then in other situations. Then regarding the community engagement, the way that we did this, I think we can reuse it in future projects, and it can be applied in different things. So we basically had from the beginning, from the proposal stage until the end, constant conversations with them, with the community engagement, with the companies that were interested in this. So this could be something that can be reused. And then Optivery solution, of course, can be applied to other use cases in other industries where multiple stops can be made. Regarding conclusions and next steps, we were able to develop the 3D drone routing algorithm, and also the second algorithm that can do the optimization for the delivery sequence for the plans. We also were able to provide a solution for the battery, although it was shown that it's highly sensitive to payload and route distancing, as it can be already imagined. Then the separation of the solution into 2 distinct algorithms, it increased the system flexibility, and it really helped in providing solutions for the algorithm. And then regarding next steps, we would like to include dynamic replanning with real-time data to basically, something that can be included in the moment, like weather or battery consumption in the moment, or these kind of things. And then also extend the current single drone planning framework to multiple drones. So in this case, we did it with just 1 drone because it's like a first idea, the minimum viable product. But in the future, if this goes ahead and we actually implement this service, it would be useful and I think more feasible economically if we do this with multiple drones instead of just 1 drone. So this is something that then in the future project we will work on to implement the multiple drone missions for this. And that's it. Thank you very much.